I see this as the result we want from applying locally linear embedding, LLE. We start with high-dimensional data, lots of features, and LLE helps us reduce it to a lower dimension, making the data easier to visualize and analyze. Think of it like making a 3D object into a 2D shadow. We lose some information, but the important shape is still there. This is your starting point. This is the data you're working with before applying LLE. It's described as high-dimensional because each data point has many features, characteristics. Imagine something like a picture. It's made of tons of tiny pixels and information. LLE helps handle the complexity of such data. LLE, or locally linear embedding, is a clever technique for dimensionality reduction. It works by looking at how each data point relates to its nearby neighbors. It tries to preserve those local relationships when it simplifies the data to fewer dimensions. It's like finding the most efficient way to represent your data while keeping its relationships. This is a super important setting in LLE. It controls how many neighbors the algorithm considers when it's working. A higher number means it looks at a wider neighborhood around each point. Finding the right number is key to getting good results. A too small number can be sensitive to noise in the data, whereas a too large number can smooth out the important details. That's why this is such an important parameter. This is the overall topic. I am focused on how changing the number of neighbors affects how well the locally linear embedding algorithm works. It's all about finding that sweet spot of complexity versus accuracy, and what that means for using LLE. This is the main quiz question. We're considering how adjusting the n_neighbors parameter affects the results from the LLE algorithm. The more neighbors you include, the more calculations the computer has to perform. It's like having to consider more people's opinions. It takes longer, but sometimes gives you a better overview. This is not always true. While more neighbors can sometimes improve the overall representation, having too many can make it less accurate, as it might smooth out important local differences. When you have only a few neighbors, any noisy or unusual points will have a big effect on the outcome. Think of it like a small group of friends. One bad apple can spoil the whole bunch. This is completely wrong. The number of neighbors you use is a significant factor affecting the outcome. It has a big impact on how the output looks. I see that increasing the number of neighbors means I need to do more calculations to find those neighbors and figure out how each data point relates to them. That directly makes the whole process slower. This statement is true. Makes sense, right? If I use only a few neighbors, my reconstruction depends heavily on those select few points. If a couple of them are noisy or outliers, they can really mess up the whole reconstruction. This statement is also true. Think of it like this. A small group of friends can be easily swayed by one loud person, but a large group is more stable. This statement is false. While more neighbors might sometimes help, it's not a guarantee. Too many neighbors might capture the big picture instead of focusing on the important local details. Imagine trying to understand a small local community by looking at the whole country. You'd miss the nuance, right? This one is also false. The number of neighbors I choose really matters. It directly affects how the algorithm works and the final result I get. It's a really crucial setting. I need to choose wisely. Think of it as the spice in your recipe. Too little or too much can ruin the whole dish. I see a smaller NNEIGHBORS value makes the locally linear embedding, LLE, algorithm more sensitive to noisy data points. Think of it like this. If you're trying to reconstruct a picture using only a few pixels, a single bad pixel will have a much bigger impact than if you're using many pixels. Similarly, with fewer neighbors, noisy data points have a greater chance to throw off the reconstruction. That's why a smaller NNEIGHBORS makes LLE more susceptible to noise. I find that increasing the number of neighbors, NNEIGHBORS, directly increases the computational cost. LLE needs to calculate distances and perform linear reconstructions for each data point and all its neighbors. More neighbors mean more calculations. That's why statement A is true. It's like trying to solve a jigsaw puzzle. The more pieces you have, neighbors, the longer it takes to put it together, more computation. I've noticed that while a larger NNEIGHBORS sometimes improves the reconstruction, it's not a guarantee. Too many neighbors can capture global patterns instead of local relationships, actually worsening the embedding. It's a bit like trying to describe a person. Using too many broad traits might miss their unique personality. I discovered that the choice of NNEIGHBORS has a significant impact on the LLE's outcome. It's a crucial parameter that needs careful selection, not something to ignore. Choosing the right number of neighbors influences how well LLE captures the underlying data structure. Locally linear embedding, LLE, is a dimensionality reduction technique. It tries to represent each data point as a combination of its nearby neighbors. The "n_neighbors" parameter controls how many nearby data points LLE considers for this combination. Think of it like this. Imagine you're trying to describe a person's face. With few neighbors, you only use a couple of nearby features. With many neighbors, you incorporate more features of their face. I'm asking how changing the number of neighbors considered in LLE affects the results. This is the core of understanding this algorithm. I've presented 4 statements about how changing the number of neighbors, n_neighbors, affects LLE. Let's evaluate each one. I believe this is true. When I increase the number of neighbors, LLE has to do more calculations to find those neighbors and make the combinations. This takes more computing time. I disagree. It's not always true that more neighbors means a better reconstruction. Sometimes, using too many neighbors could blur important details and end up creating a worse representation. I think this is true. If I only use a few neighbors, noisy data points could have a big effect on the representation. It's like if only a few people describe someone and one of them gives inaccurate information. It can skew the overall description. I think this is false. The number of neighbors is a super important choice in LLE. It greatly affects how accurate the low-dimensional representation is. Locally linear embedding, LLE, is a dimensionality reduction technique. I use it to transform high-dimensional data into a lower-dimensional space while preserving the local neighborhood structure. The "n_neighbors" parameter is crucial because it controls how many neighboring data points I consider when reconstructing each point. Think of it like this. I'm trying to build a small neighborhood for each data point, and "n_neighbors" tells me how many houses are in that neighborhood. This problem tests your understanding of how the "n_neighbors" parameter affects the LLE algorithm. I'm asking you to identify which statements about the impact of "n_neighbors" on LLE are true. A smaller "n_neighbors" means I'm only looking at a small number of nearby data points to reconstruct each point. If a few of those points are noisy, incorrect or outliers, they'll have a big impact on my reconstruction. It's like trying to build a house using only a few bricks, and if some are damaged, the whole structure suffers. Increasing "n_neighbors" doesn't always guarantee better reconstruction. While using more neighbors can sometimes help, too many neighbors can make the algorithm focus on global structure, potentially ignoring important local details. Think of it as trying to find a good friend. Using too many neighbors could make it difficult to find the right person. That's incorrect. The "n_neighbors" parameter has a huge impact. The number of neighbors used profoundly influences the results I get. Ignoring this parameter is like trying to bake a cake without checking the temperature. The result is unpredictable. Increasing "n_neighbors" means I have to do more calculations for each data point. I need to find more neighbors, making the whole process slower and requiring more processing power. It's like building more houses. It'll take more materials and time. This refers to the method for finding the nearest neighbors. "K" is equivalent to "n_neighbors". The algorithm finds the k closest data points to each point for use in the local linear reconstruction. I'm essentially finding the closest data points to each point to build its local neighborhood. Once I've identified the neighbors, I reconstruct each data point using a linear combination of these neighbors. This means I'm approximating each point using a weighted average of its neighbors. This step helps preserve local neighborhood relationships. After reconstructing all points, this technique produces a new representation of the data with fewer dimensions. It maintains important relationships found in the original high-dimensional data. I basically reduce the number of variables needed to describe the data without losing too much information. This is the data that has many variables, much more than needed. Dimensionality reduction methods like LLE help reduce complexity. I might have lots of measurements of something that could be represented with much fewer variables. I can't show a visualization here, but imagining points in a high-dimensional space then being projected onto a lower-dimensional space will illustrate the essence of the LLE algorithm. It maintains neighborhood structures. I see that increasing the number of neighbors directly increases the computational load because the algorithm needs to perform more calculations to find the neighbors and reconstruct each data point. Think of it like this: if you only need to consider one neighbor for each point, that's easy. But if you have to check 10, 100, or 1,000 neighbors, that's much more work, right? That's why statement A is true. The choice of the number of neighbors significantly impacts the outcome because it directly affects how the algorithm operates and the resulting low-dimensional representation. It's not a minor detail, it's a crucial setting that needs careful consideration. Think of it like choosing the right lens for your camera. The wrong lens and you get a blurry picture, a distorted perspective. Statement D is wrong because it completely ignores the impact of this important setting. A smaller number of neighbors makes the algorithm more vulnerable to noise. Imagine you're trying to find the average height of people in a room. If you only ask 3 people, and 2 of them are unusually tall, your average will be way off. With more people, the effect of those outliers is reduced. Similarly, a small number of neighbors means a few noisy data points can have a big effect on the result, making statement C true. The question explores how many neighboring data points the algorithm considers when creating the lower dimensional representation. It's a core parameter affecting the algorithm's efficiency and accuracy. Getting this right is essential for a good result. It's like choosing the right tools for the job. Isn't it exciting?